Welcome to the TFAWS 2022 active thermal session. Today, running the session is going to be myself, Michael Elmore, and then you'll also see on the panelist list there's Tom Limeculer. Okay, so let's go ahead with our first presentation. So our first presentation for today is simulation of heat transfer of aluminum 2O3. I'm sure I should know what that chemical formula is, but I don't. Water nanofluid effect volume fraction.
So good morning. Good morning, everyone, and thank you for listening in. Our study here is entitled Simulation of Heat Transfer of Aluminum Oxide, Water Nanofluid, and we want to study the effect of volume fraction. I want to acknowledge my graduate student, Amir Reza Radmanesh, who did the bulk of this work. This particular study, is not really new in the sense that it has not been done. What's new is we're trying to be systematic about it, and the reason for that is that there is a lot of disagreement on the different aspects of nanofluids, their properties, the different correlations people came up with for properties and for heat transfer behavior of nanofluids and so on. So that's why we're doing this ourselves. So we have some sort of ownership of of information and trying to be systematic and build on sort of from ground zero. We gathered the disagreements as we did our literature search and looked at many papers, and we realized that we don't know which paper to trust and which results to trust. So there were a lot of divergent information. That's why we decided to do this. But as you know, nanofluids have been around for a very long time, 15, 20 years, or a little bit more, actually. And they started getting interest from the thermal science community, from the heat transfer point of view. And in case someone doesn't know what a nanofluid is just a suspension of high conductivity nanoparticles in a base fluid in order to enhance the thermal conductivity of the base fluid. And the base fluids are usually the common coolants that we use in order to, carry heat transfer and do heat exchange. Some of the common coolants, for example, are water. We use a lot of water in many applications, but other base fluids are things like engine oils and so forth, and engine coolants. We also can form nanofluids by dispersing these relatively high conductive nanoparticles in phase change material and enhance the conductivity there. And we do that also for refrigerants. So we have a whole range of nanofluids using different coolants or different base fluids, as I mentioned. In terms of what nanoparticles that have high thermal conductivity that have been in use, usually metals and metal oxides. For example, here we're presenting aluminum oxide. There are more exotic and more expensive nanoparticles, such as, the carbon base type of nanoparticles. But, the short story is, our common coolants have low conductivity and therefore heat transfer is weak and can be improved by increasing the thermal conductivity of the working fluid. When we do that with nanoparticles, we actually get also an increase in the heat transfer coefficient uh, for forced convection. So the issue is just not only increasing the thermal conductivity, but researchers have noticed an increase in the convective heat transfer coefficient as well. The penalty, and it's a small penalty, is an increase in viscosity of the working fluid and therefore, and the density, and therefore we get, a penalty in terms of pressure drop and so forth. So this is just a quick background. And in terms of applications of, the enhanced heat transfer of nanofluids, we can look at and consider, for example, vehicle thermal management systems and power generation and solar collectors and cooling of electronics and fuel cells and things like that. So the whole range of, the cooling problems that we face in different industries. Yeah. So this is a first step in trying to understand uh, this enhanced heat transfer. So we took a very simple problem. We took a pipe, an open pipe with nothing inside, and we subjected it to heat flux. And the dimensions of this pipe are 5.25 centimeter internal diameter, and the length of the pipe is 15.24 centimeter. We put a constant heat flux on this pipe, and the heat flux, as you see in the screen, is 74,948 watts per meter squared. And we said we're gonna send in deionized water as a base case, then our nanofluid with different concentrations, as I will show you in a minute. The inlet velocity was 0.029 meters per second, and it was flat velocity profile, uniform velocity profile. And we said, the temperature, the inlet temperature is about room temperature, or exactly to 98 degrees Kelvin. So with this, we did simulation using ANSYS Fluent, yes, and we assumed laminar flow, and we made sure our velocity and the Reynolds number are within the laminar flow conditions. We went ahead and wanted to see when the results of our simulation become independent of the mesh, some routine check in order to see the goodness of our simulation. Everybody who's done a simulation, I think, knows that. Okay, so now I have to talk a little bit about the assumptions that went into the simulation of nanofluids heat transfer. Well, because physically you have two phases in a nanofluid, you have, in this case, you have the water, and then you have the aluminum oxide particles swimming or suspended in the water. You physically have two phases. And there are two approaches as to how you model this fluid. The one approach is to use a single phase model and assume that you just have one fluid and it has the appropriate properties, okay, by doing some sort of weighted average combination of properties of water and the aluminum oxide, and then treat your fluid as a single uh, fluid or a single phase fluid with these new calculated properties. And you also assume that within the nanofluid there is thermal equilibrium locally, meaning the the particles, the solid nanoparticles, and the water next to them are at the same temperature. If you do this, then you solve mass momentum and energy equations for conventional liquids, right? Albeit with the new thermophysical properties for the nanofluid. The other approach or the other model of this two-phase system is actually called the two-phase model, where you would treat uh, the two phases separately, and then the equations are gonna be different because you have to do that and do the solution for each phase. In our literature search, we found out that many of the authors said, listen, it's not going to make a big difference really, and the one phase model is good enough for the most part. So we went with this model in this particular study. Okay, so here are the cases we study, and I'm sorry about the white on white, but this table shows you the different concentration phi of the nanofluid that we study. So we had 0.25% by volume of the nanoparticles divided by the total volume of the nanofluid, and then 0.75 and then 1.5. Now, we went ahead and calculated the different thermophysical properties that we need, viscosity, conductivity, specific heat, and the density, of course. Now, I have to mention one thing here. If your concentration is too low, you're not going to get a lot of heat transfer enhancement because you're using a very small fraction of the high conductivity nanoparticles. If your volume fraction is more than 1.5, then you have too much solid particles and you get into issues of sedimentation and so forth. So we have to work in this narrow range, and we have to have a compromise. We do want enhanced heat transfer, but we also want to avoid uh, sedimentation and other issues of having too much solid particles suspended in the fluid. So I'm just gonna present a couple of cases that we did. And by the way, these thermophysical properties were calculated using some of the very widely used correlations in the literature, and you can find differences actually in the paper itself. So, in terms of result, and this result is for this Reynolds number, okay, and we're looking at results for the different concentrations, going 0.25, 0.75, and 1.5% by volume. So we see a couple of things here. And the base case is water, and it's shown by the solid gray markers here. And the red squares are for this very low concentration. So the very low concentration of 0.25% by volume doesn't really produce any appreciable heat transfer enhancement. It's just too little. As we increase the concentration to 0.75%, we see some enhancement, and the enhancement actually goes up when we increase the concentration to 1.5% volume fraction. So there is a nice big jump, and we're looking at the surface temperature as a marker of the enhanced heat transfer. Okay. In the case for the other Reynolds number we're presenting here today, we saw similar effect for the different concentrations. And we see the enhancement shown at this higher Reynolds number. And the percent in enhancement is different, and it depends on the Reynolds number. So there seem to be other effects that depend on the velocity of the fluid for a given concentration. So this requires further investigations, and which we are doing now. We want to study other concentrations, and we want to study other Reynolds number, and we want to try to find out what kind of effects that are present and not accounted for when the Reynolds number increases. So this is really all I have for today. And we can entertain some questions. Excuse me.
Okay, thanks. Yeah, if anybody has questions, feel free to put them in the chat box, and we can read them out here. I did have a question just for myself. Do you have any considerations as to what the particles in the fluid might do mechanically, like in terms of damage to pipes, or assuming if you turn up the concentration a lot, right? Any particles you have are going to be going through a pump or something, and that might have some harm there.
Yes, that's a very good question. The simple answer is no, because the size of these particles is, 10 to minus 9 meters. They're in the nanoscale. So if you look at them physically, and we bought some of them, they look like dust. And so the nanofluid looks like murky water, and it behaves like water, and it doesn't damage any of the common water equipment like water pumps and piping and things like that. But I imagine if you're looking at very intricate systems with very very small dimensions, right? Like micro channels, for example, where the size of the conduit is getting closer to the size of the nanoparticle, there may be some issues. Or microfluidics, for example, there might be issues there, but we're not looking at that.
Okay, thanks. And we did have one question pop up here. Precipitated nanoparticles can behave as nanofins, also at high concentrations greater than 1% mass fraction. The Newtonian neat solvent can become non-Newtonian. They're wondering if your model can incorporate those effects.
We haven't, but we are aware of these effects. We are aware of the non-Newtonian behavior. I don't think it happens necessarily at 1% volume fraction, but it for some nanofluids at certain concentration, yes, the behavior becomes non-Newtonian, which is, a problem. And so we didn't look at that yet. We didn't encounter this here.
Okay, here the chat is starting to explode a little bit here. So next question, you might have already answered this from the question I asked you, but someone asked here, what about erosion damage?
That is an issue with nanoparticles in general, right? And we didn't study this. There is also fouling. That's another related sort of damage. People are aware of this. We didn't look at this problem, but we know that it can be there.
Okay, cool, thank you. Next one here, for a given volume concentration, does it make a difference whether you have a large number of small particles or a small number of large particles?
We have to stick to the nano size. So when we say nanofluids, it means your particles have to be less than 100 nanometers. Okay? And so existing like commercial nanoparticles come, with different sizes, but they are all less than 100 nanometer. We didn't look within the 100 nanometer range. For example, you can buy particles that are 50 nanometers in diameter, or you can buy particles like 70 nanometers. We ourselves here didn't look at that effect, but there are papers in the literature that look at the effect of nanoparticle size on the heat transfer and properties and so forth.
All right, excellent, thank you. Here we have, you got a few more here, 3 or 4 more. Very interesting presentation. Was the particle size distribution a part of the correlation estimation for the thermal properties of the nanofluid?
No, it wasn't. And from our literature study, there are many questions to be answered. And this is one of them, actually. You find these correlations, and different people are, not as meticulous at reporting their conditions. And most of the studies focused on a particular uh, nanofluid, right? And so there are a lot of experiments and correlations to be produced that can cover a whole range of concentration, nanoparticle size, uh, and so forth, right? And unfortunately, uh, there aren't enough information uh, comparing apples to apples. So you may find a paper that studied nanoparticle size for aluminum oxide, but then the other paper studied, volume percent effect for another nano particle and so forth. So it's really hard. And if someone in the audience is looking for, good problems to solve, get into nanofluids and, study them systematically and give us some trustworthy correlation that are systematically produced and cover a wide range and different effects.
Okay, thank you. And then your next one here, how much is the improvement due to the capacitance increase of the fluid versus the conductance increase of the fluid? Or is it mainly the fluid dynamics of the mixture that changes the transfer coefficients, meaning that even mixing a non-conductive particle would enhance the performance anyway?
From what we read in the literature, the main enhancement is in the thermal conductivity, and therefore, if you look at the literature, the majority talk about enhancement in thermal conductivity. I don't think the capacitance plays a big role. The major role is played by the enhanced thermal conductivity, and second to that, there seems to be an enhancement in the heat transfer coefficient. Now, the heat transfer coefficient is a complex function of many variables. So I can say, for example, it wouldn't be surprising to find out that the heat transfer coefficient is a function of the particle size, for instance, because there is mechanical mixing, there is dispersion of the nanoparticles as they swim and bounce and so forth in the base fluid. So I imagine some of these effects will show up in the enhanced heat transfer coefficient and things like dispersion and so forth. But the main player is the thermal conductivity.
Okay, thank you. And got still a couple more. It looks like you used the metric of fluid surface temperature for enhancement of heat transfer. Did you consider the use of bulk fluid temperature for the metric of heat transfer enhancement? From a practical perspective, have you considered what would be the more appropriate metric given that the conductivity is increased by about 4% from quarter percent to 1.5% volume fraction?
Well, the bulk temperature uh, can be obtained from the simulation, and it's a good marker for the enhanced heat transfer. Yes. And the overall heat transfer coefficient would be uh, a good measure. We didn't do that, but this is something to be done and looked at. We're starting this and we're taking baby steps, but these are very good points.
Okay, thank you. This one, I'm not sure if it's more of a comment than a question, but it has here, smaller particles provide more surface area for heat exchange. I'm not sure if they're referring to the particle, we were talking about erosion earlier. I'm not sure if that mean they're referring to the particles depositing on the wall or something of that nature, but I don't know if you have any comments on that.
Yes, I agree. The more surface area, the better the local heat transfer, even though we're talking about a single phase model, but the physics at the small scale, yes, you would have more surface area, so there might be good heat transfer interactions between smaller nanoparticles and a base fluid.
Okay, thanks. And I think we have one last question. And right on time. It's like 9:30. Does the addition of metallic nanoparticles in the fluid have an effect on electromagnetic interference?
Yes, yes, it does. And some people studied that. They studied magnetized systems with nanofluids. So, and they try to use magnetism to enhance heat transfer of nanofluids. And in critical systems used by NASA, for example, they have to worry about this issue.
Okay, thank you. I'm not seeing any other questions. Oh, we just got one here. Okay. Won't the nanoparticles distribution have an effect on thermal conductivity? I think that you might have already answered that one, but
Yes, it does. So that's another level of, intricate study. If you look at a given cross-section of the pipe that we studied, you can go further and say, okay, I have more concentration of nanoparticles close to the wall, for example. You can do that. And, you know, that happens. I don't think it has a major effect, but that's a hunch. But yeah, you can look at the concentration and the difference in thermal conductivity in different regions. Sure.